All right, let's talk about something that's all around us, all the time, but we barely ever think about it: relative motion. I mean, it's everywhere, from just walking down the street to a pilot trying to land a plane in a storm. To really get a feel for it, let's kick things off with a super simple question.
Okay, let's do a quick thought experiment. Imagine you're on the highway, right? You're cruising along, doing a steady 70 miles per hour. The car in the lane next to you starts to slowly pull ahead. You know they're going 72. So the question is, from your perspective, sitting in your car, how fast does it feel like that other car is moving?
Yeah, 2 miles per hour, right? Of course. It feels totally intuitive. From your point of view, that car's just creeping past you. But here's the kicker. Is that the only right answer? Let's tweak the scenario just a tiny bit. What if we ask how fast that same exact car is moving, but this time relative to a bird that's flying overhead? Or, just someone standing still on the side of the road. All of a sudden, that 2 miles per hour answer, it just doesn't feel right anymore, does it?
And that is the whole point. See, the answer to any question about motion isn't just one number. It completely depends on your point of view. This is the fundamental idea we're going to dig into today, that all motion is, well, relative.
So this point of view thing is obviously super important. But how do we talk about it in, a more scientific way? Well, physicists actually have a special name for it, and it all comes down to choosing where you're watching from.
They call it a reference frame. Think of it as the background you're measuring everything against. It's your anchor point. It's the simple answer to that crucial question. Relative to what?
Most of the time, we don't even think about it. We have a default reference frame that we just use, and that's the Earth. When you say a car is going 70, what you really mean is 70 miles per hour relative to the ground.
But here's the really cool part. You can pick anything to be your reference frame. Seriously. It could be the train you're riding in, or the air a plane is flying through, or you could even get really big and use the sun as your reference frame and watch the Earth spin around it. And the crazy thing is, the laws of physics, they work perfectly no matter which one you choose.
Okay, so we've got this idea of a reference frame locked in. Let's put it to work now in the simplest case we can think of. Just stuff moving in a straight line.
So, here's a classic physics problem. Picture this. You're on a train and it's chugging along, heading east at 10 meters per second. You decide to get up and walk towards the back of the train at a pretty relaxed 2 meters per second. So, how fast are you moving? Well, by now you know the answer is, it depends.
And we can figure this out with a really neat little equation. Basically, your velocity relative to the Earth, we'll call that VPE, is just your velocity relative to the train, VPT, plus the train's velocity relative to the Earth, VTE. And check out this cool little trick with the subscripts. The two inside letters, the T for train, they match up. It's a great way to double-check that you've put the puzzle pieces together in the right order.
And this shows the difference so perfectly. If your reference frame is the train itself, well, you're just walking at 2 meters per second towards the back. Simple. But for somebody standing on the ground, watching this whole thing go by, they see the train's 10 meters per second east, but then they subtract the 2 meters per second you're walking west. So to them, you're actually still moving 8 meters per second east. How wild is that? Two totally different answers, and both are 100% correct.
All right, that makes sense for things moving in a straight line. But, the real world is a little more complicated than that. So let's level up and see how this whole idea works when we start moving in 2 dimensions.
Okay, the formal rule for this can sound a little academic, but don't let the fancy words fool you. It's the exact same idea we just used with the train. All it's saying is that to find something's velocity in one frame, you just add its velocity in another, moving frame, to the velocity of that frame itself. It's all just adding vectors together. So let's put this to the test with a real-world problem pilots face all the time. Imagine a pilot. Their mission is simple: fly the plane due north. But there's a catch. A nasty crosswind is blowing in from the northeast, and it's constantly pushing the plane off course. So here's the puzzle. If the pilot just points the nose of the plane straight north, that wind is going to shove them way off course down to the southwest. So to actually make progress and fly north relative to the ground, which way do they have to point the plane? And guess what? We solve it with the very same equation. The plane's final velocity over the ground is just the sum of its velocity through the air plus the velocity of the air over the ground. You can think of it like this. The pilot controls the plane's speed and direction through the air with the engines. The wind controls the motion of that air. And when you add those two things together, you get the plane's true path. So to fight back against that wind coming from the northeast, the pilot has to aim the plane a little bit east of north. It's like they have to aim into the wind. By doing that, they're creating a motion that perfectly cancels out the sideways push from the wind, and the end result is a path that's straight north over the ground below.
So, whether we're talking about cars on a highway or planes in the sky, you can see how this one simple idea is incredibly powerful. Let's wrap things up by boiling it all down to a few universal rules.
Yeah, this right here from our source material really lays out the key principles perfectly. Let's quickly go through them.
Okay, rule 1, you always have to state your reference frame. You can't talk about motion without it. Rule 2, velocity is always relative. Its value changes depending on your reference frame. Rule 3, the way you switch between frames, it's always vector addition. And finally, there's a really interesting fourth point. As long as you and I are moving at a steady speed compared to each other, if we both look at a third object accelerating, we will measure the exact same acceleration. Pretty cool. Now, this whole system works beautifully for, cars and planes and trains. It's called Galilean relativity. But it opens up a really fascinating door to a much bigger question. What happens when you start moving really fast? Like, what if our train wasn't going 10 meters per second, but 90% of the speed of light?
Well, that's when our nice, simple rules for adding velocities start to fall apart. And that's where a guy named Albert Einstein comes into the picture. But that is a whole other mind-bending story. For today, the big takeaway is this. In the world we live in, motion is never absolute. It's all a matter of perspective.